Hello, everyone. Welcome back to our journal club. This is an unusual time, but thanks for joining us. Today we'll have Nadine tell us about fast radio bursts. Take it away.
Okay, so I think everyone in the room probably knows me, Nadine, in case you missed it. And I'm going to be talking to you today about something that I am definitely not an expert in, but I still think is pretty interesting and has a lot of open questions that are worth thinking about. And that's FRBs, or fast radio bursts. So before diving into the specifics of how do you formulate a model for FRBs, or what exactly are they, these are the properties that have been observed for FRBs, or this is essentially what makes an FRB an FRB. And it's pretty much summed up in the name. So first thing, they're fast. They usually last for a few milliseconds, and they typically originate from extragalactic or cosmological distances. And since FRBs have been first observed, there have been hundreds of sources that have been added to FRB catalogs, some of which that have been specifically localized. And at this point today, we have, FRBs are a real phenomenon that exists, that are taken seriously by the astrophysical community. And one of the reasons they're also interesting is the very last part of the acronym, which is the burst part. They're highly energetic pulses that are observed in the radio. And throughout this talk, what I want you to sort of try to think about is how can you generate a burst with such high energy that only lasts for a few milliseconds. And last thing that is quite interesting, as more and more observations have poured in, we've seen that some of these sources show repeated bursts. So that's also fun and exciting. So we can start off by the very first burst that was observed, which is the famous Lorimer burst. And this is actually detected by the Parkes 64-meter telescope in 2001, but it was only analyzed in 2007. And that sort of tells you something about how we treat our data. The reason people didn't realize this giant pulse is because radio surveys usually search for periodicity because they're looking to study pulsars. And this was a singular burst, so it was completely skipped over and only realized when a grad student was looking through archival data. So this sort of tells you that FRBs weren't discovered because we made fancy new telescopes or detectors that had super high resolution or really cool properties. It was simply because we started to look and treat our data differently.
So was this the first, the first one ever measured, or the first one ever analyzed, or both?
So it's I guess it's hard to say first one ever measured, because then you'd need to look at every single thing. But I think it's technically the first recording of an FRB by a telescope that was at least analyzed. And what was interesting about this burst is in the radio we're used to, again, pulsars, and this pulse had a lot more energy than that you would expect from a typical pulsar, and it didn't show any periodicity or repetition afterwards. So fast forward to 2011, 4 more FRBs have been detected and analyzed, and this sort of affirmed the existence of FRBs, and that allowed us to calculate an event rate density for how often these events take place. So on the left, okay, I have a cursor. This is sort of a much more updated plot of all FRBs. And you can see that they're pretty much like isotropic in space. And a lot of these go up to really high redshifts, which in this case means like redshift 1. Depending on your field, that might be high, that might be tiny. And their event rate density was around 10 to the 4 events per gigaparsec cube per year, above a luminosity of 10 to the 42 ergs per second. And to give you a reference for what that number means, that's really high. That's a lot higher than most catastrophic events that take place in the universe. And it's higher or relatively comparable to the supernova rate. And supernovas happen everywhere all the time. So that sort of tells you that the likely engine that's driving these bursts is probably not a catastrophic event that destroys the source after. And as I was mentioning before, some of these bursts, unlike the very first burst, were observed to repeat. And around 20 out of roughly hundreds of FRBs so far have been repeaters. And I think while I was writing this slide, there was like another repeater being reported. So repeaters are quite interesting because, first of all, they introduce more questions to the puzzle. So the first question is, if you've observed some to repeat, do all of them repeat? And if all of them repeat, does that mean that the ones we don't see repeating just have a really low repetition rate? And how, like, why would that happen? What triggers repetition versus non-repetition? And then you could also go to the other argument, which is maybe you just have two different classes of FRBs due to completely different events that are happening. Some that are catastrophic, so you don't see repeated bursts coming out of them, and then some that aren't, so you could still see other bursts from the same source.
So can you, what is the timescale of repetition usually for the repeaters?
So it depends. If you're asking about periodicity, some, I think I have cool.
Okay.
So this is sort of like, because we're used to pulsars, we're like, okay, if something repeats, then it should have a period. So people started looking for periodicity on the order of like a few seconds or less, and they couldn't find any trend in periodicity. And these sources, I think there were 2 sources for which we detected a specific period, and that ranged from like 16 days to 160 days.
But it's not like a precise periodicity, right? So
no, I think there are relatively high like uncertainties when it comes to that. But in general, kind of tells you you're not in the ballpark of like rotation periods of like a pulsar or something, and it points you more towards maybe like binaries or like precession models that maybe due to some interaction between the other body, you have this giant burst coming off. And I think these 2 diagrams will make a little bit more sense as I explain some of the mechanisms, but there's sort of hundreds, okay, maybe dozens of proposed mechanisms for what are FRBs, how are FRBs, who are FRBs, and this is a sample of those. So to sort of try to understand what we know about fast radio bursts, we can go back to the first burst and try to see what kind of information we could extract from the spectrum. So there are 3 main pieces of information that you can get from the picture on the right. First is how long the burst lasts for. Second is this frequency sweep in time that you see in the larger plot. And from these 2, you can combine information to start estimating the energetics of the event that gives rise to this burst. So let's go through them one by one. So the burst duration. So on the right are a few spectra for typical FRBs, and some of them have substructure, but you can sort of ignore that for now. And the main thing they all have in common is they only last for a few milliseconds, typically 5 to 10 milliseconds on average. And what that allows you to define is some characteristic length for the size of the emission region. So you might have heard this argument in high energy or in other astro classes, where if you have some emission region of some finite size, then the photons being radiated from the front of this region will arrive at your telescope faster than the ones that are at the end. And that basically causes your pulse to smear across some delta t time equal to the pulse width. So that lets you put some lower limit on the size of this region, which is simply going to be c times the pulse width. So if we're dealing with millisecond pulses, then that gives you a characteristic length of around 10 to the 7 centimeters. And that's tiny. So that points you towards really compact sources. So you start immediately thinking of, okay, maybe I'm dealing with a neutron star or a stellar mass black hole. And you don't need to consider things that are much larger. So that's sort of the information that you get from the burst duration, sort of the physical size of your emission region. And from there, we could start focusing on this quadratic frequency sweep. And if you've worked with pulsars or are familiar with pulsar emission, this is a very common feature when you're observing in the radio. And it's due to time delay because of propagation of the emission through space. So, okay, this is tiny. I don't know if anyone can see this. But essentially, if you have an event that takes place somewhere far away, and it's emitting a broad range of frequencies all at the same time, then as these waves propagate, they will be slowed down at a rate according to their frequency. So higher frequency waves would be slowed down less than lower frequency waves as they reach your telescope. So what you end up seeing on your frequency channels is something that looks like this, which is, again, super tiny, but you see higher frequencies arriving earlier, and you see this sort of quadratic trend. And if you've not seen this derived in class, today's your lucky day. So it's kind of a fun, easy derivation that you can kind of do that also tells you a bit more about the constraint that such a time delay would give you. So again, if you're propagating through something that is not just vacuum, then your group velocity is not going to be c, but is going to be c times your refractive index that corresponds to this optical medium that you're propagating through. And in the case of propagation through plasma, that refractive index is defined as this expression, where nu p is your plasma frequency and u is the frequency of your radiation. And if the plasma frequency is not imprinted in your brain, it should, but what you pretty much need to notice is this electron number density dependence. So nu p depends on the electron number density to the 1/2. So that's all cool. Let's try to derive the time delay equation. So it's just simple propagation. You're propagating some wave at a specific frequency through some path length dl, and you plug in the expression for the group velocity and do a first order Taylor expansion. So you end up with this expression here, and if you want to get the time delay, not just the arrival time, you just subtract that by dl over c. But if you notice this dependence here, so this depends on the plasma frequency squared, so it's proportional to the electron number density along your line of sight. So we can define this other property, the dispersion measure, which you'll see thrown around a lot in FRB literature or in Astro in general with observations, which is simply the integral along your line of sight of the number density of electrons. So we can combine this expression into something that only depends on the dispersion measure, which is going to be a constant for a given observation, and have this mu to the minus 2 dependence, which results in that quadratic sweep.
And the dm is in what units, or? Like?
So it's gonna be, it's usually written down in funky units where you have like centimeter to the minus 3 parsec, because people prefer to measure like the DL in parsecs, but number density is still measured in like centimeter to the minus 3. But technically it's like centimeter minus 2.
And that's the number you report when you plug it into this formula, or?
Yeah, so here it's the dispersion measure would be centimeter minus 3 parsec and using gigahertz,
Okay.
to match this time. And you can get constraints on the electron, the DM from other observations that come from locations relatively close to your source. So this allows you to sort of determine how far away the source is. And you can also like minimize that with a bunch of different algorithms that people use. But there's even more and more time delay that you experience due to other effects. So we've had DM, now we have RM, which is rotation measure, and it has this frequency to the minus 3 dependence. And this essentially arises due to Faraday rotation along your line of sight. So if you have some linearly polarized wave that's propagating through a magnetic field, it will experience some phase shift that is frequency dependent, and that would result in a time delay that's proportional to u to the minus 3. And just for reference, the rotation measure is defined very similarly to DM, but with a magnetic field stuck in there. And why do these matter? Well, using RM and DM, you can constrain the average magnetic field along your line of sight. So by definition, the average magnetic field is just the ratio of RM to DM. And that's important for FRB measurements because people have observed really high RMs for some radio bursts that are much higher than you would expect just from propagation. So in the usual scenario, you expect that there's some radiation coming out of your source, and then along your line of sight, there's some Faraday screen with a magnetic field in there that's giving you the time difference. But these really high rotation measures sort of tell you that the wave is initially also propagating through a highly magnetized plasma, and therefore shows higher RMs than we expected. But also, people have observed RM variations, especially in repeaters, and you wouldn't expect the ISM to cause that because that, we assume, is roughly stable on these timescales. So this has to be related to somewhere close to your emission region. So it must be highly dynamical, at least in terms of the magnetic field around it. So now that I've spent quite a while talking about time delay, after you subtract that from your spectrum, you sort of expect like a clean burst to show up. But there's even more frequency space, more frequency sweep, and this is known as the sad trombone effect. I should have played a sad trombone sound, but oops. And again, it's this, after you clean up all the propagation effects, you see this downdrift of pulses with frequencies. And yeah, this is shown in repeated bursts. And because you've already accounted for propagation, this is likely due to the intrinsic radiation physics that's releasing this emission. So now that we've covered the time delay component of the spectrum, we can start talking about the actual energetics of fast radio bursts. So what you're observing in your telescope is some specific flux across a frequency band, and this is pretty much the specific intensity times some viewing angle. And you can estimate this viewing angle as the ratio of the size of your source, which you could determine from the pulse width, to the distance to the source, which you could have constraints for using DM and other measurements. And because we're in the radio, so we're in the Rayleigh-Jeans limit, you could use that to define some brightness temperature. So if we rearrange this set of equations and plug in some typical values for FRBs, we get a whopping 10 to the 36 Kelvin as a brightness temperature for FRBs. That's a lot. And specifically, if you put this on a luminosity frequency pulse width diagram, which if you're not familiar with what this means, here these axes basically allow you to plot these lines of constant brightness temperature and therefore characterize different radiation mechanisms. So if we think about brightness temperature in general, it's usually used for black body radiation. So it's the temperature you expect your emitters to be at if they're at thermal equilibrium with each other and emitting these thermal photons. And this pretty much constitutes this part of the plot. So you can go up to temperatures of 10 to the 4 Kelvin with black body radiation or thermal mechanisms. And you can expand that a bit more to synchrotron-like emission, which is if you have some field that's accelerating these particles, so driving them out of equilibrium, you can have higher and higher luminosities, so therefore higher brightness temperatures. And that's usually the mechanism that is emitted from AGN disks. But the issue with synchrotron is that it is susceptible to self-absorption. And you start caring about self-absorption when the brightness temperature becomes comparable to the kinetic temperature of the particles. So they start upscattering and absorbing some of this radiation that essentially gives you a power law that breaks down very fast and therefore limits the total luminosity that you can emit. So FRBs are here. How do we do that? And the hint is in this bolded capital thing here, which is you get coherent emission. And essentially, incoherent versus coherent emission is relatively simple concept to discuss, where the typical emission that we're used to dealing with is all incoherent, where you have a bunch of particles randomly spaced, emitting at random phases. So the resulting power that you observe is simply going to be n, where n is the number of particles, times the energy each one is emitting. All simple physics makes sense. But with coherent emission, if you organize the particles such that they emit in phase, whether due to how they're localized or their position in the momentum phase space, their amplitudes would add coherently. And because power is proportional to the square of the amplitude, then you start getting powers that are proportional to n squared. And that allows you to push that brightness temperature level a lot higher, because then your dependence is much steeper. So now that we've had all these sort of astrophysical observational facts that you see from the data, how do we begin to formulate an FRB model? So for an FRB model to be sort of promising, it needs to satisfy two main properties. First, you need to satisfy the global properties, which are the event rate densities. You can't have something that's super rare. You need to satisfy the energy budget that would be required for such a high energy burst, and you need to account for the associated dm and rm of the source. And second, you need to come up with a radiation mechanism that accounts for coherent radio emission, high brightness temperatures, and would last for a few milliseconds. And essentially, if you think about the most debated FRB models, they come in two main flavors. So you have the magnetospheric models, which are sometimes called pulsar-like models, and you also have relativistic shock models, which are GRB-like models, or gamma ray burst-like. And if these two words mean nothing to you, here's a diagram to sort of demonstrate what they mean. And essentially the difference between these two models is, where does the radiation come from? How far away from your engine source does the radiation start? And in pulsar-like models, like pulsars, you assume that this is radiation coming from very close to the surface of your neutron star or magnetar. And it's essentially being emitted due to particles that are accelerated along some magnetic field lines. And for the GRB-like, you're assuming that you have some engine that's ejecting some charged particles or some ejecta off its surface, and then this collides with some remnant of an old explosion, and that triggers the formation of an FRB as it propagates through this shock. And I don't think I'll have time to go through all the different proposed models in each of these, so I'll give you a flavor by talking about the most popular for each subtype, or at least the ones that I like talking about. So for pulsar models, what you see people talking about a lot is coherent curvature radiation. So here you have your, where's my cursor? Okay. You have your rotating neutron star, where it's rotating along this axis, and this is its magnetic axis, and the cylinder that you see around it is simply the light cylinder. So now that we've defined the constraints of this light cylinder, then this defines some field lines that would be open and some magnetic field lines that would be closed. So here you have the closed magnetic field lines, which is your force-free magnetosphere that's just rotating around, and then you have these open field lines that close infinitely far away. And these open field lines essentially define a region on the surface of the neutron star called the polar cap. And this is just the cap where all the open field lines end up. And what this allows you to have is that you can accelerate particles along these open field lines, and they could then escape as they're being accelerated. And this is essentially just synchrotron radiation, but with a different flavor, where in synchrotron, you're emitting radiation because you're gyrating along a magnetic field line. Here, you're not gyrating along it, you're literally just being accelerated along the direction of the magnetic field line. So that's pretty much the difference between something that we're familiar with and like curvature radiation. And there's the coherent part of the model, which is that you need to generate bunches of charged particles that are being accelerated. And to generate these bunches, you need to invoke something called the two-stream instability, which I won't get into a lot of detail, but it's essentially a resonance instability where if you have two streams of particles passing next to each other, you could construct velocities where the denominator of like the growth rate explodes, and you just have an instability where the density fluctuation is supermassive, and it grows very quickly. So that allows you to create these bunches to allow for a high enough power to be emitted using this mechanism. And what's nice about this is, first, because this model was studied a lot for pulsars, so there's already a lot of literature about it, but it can account for this frequency downdrift or sad trombone effect quite naturally, where if this is your line of sight, for curvature radiation, the frequency that you emit depends on how curved the path you're traveling along is. So if you assume that a bunch of particles were simultaneously ejected from the surface of the neutron star, the ones that you will see first are going to be these ones. So the ones that are closer to the neutron star. These will intersect your line of sight first. And then those that will intersect it later would be emitting at a less curved part of the field line, and thus emit lower frequency waves. So this naturally explains why high frequencies arrive faster than low frequencies. So all of this sounds great.
Could I ask a question?
Yes.
So for the you say you need the two-stream instability. At least this is a good way to make bunches. So what are the two streams?
So you could have two streams of, for instance, electrons and positrons that are traveling in opposite directions or being accelerated in opposite directions. You can also have two streams due to particles having different energies due to the acceleration mechanism itself that you invoke. So you could have older particles that have kind of slowed down a bit, and these new, more energetic particles, or vice versa, depending on the mechanism. Cool. Okay, so some drawbacks for this model is because you're generating these particles that are emitting really high energies, they have a very fast cooling time, and they wouldn't really last for 5 milliseconds worth of radiation. So a critical requirement for this model is you need some parallel electric field that continuously accelerates these charges as they're passing by to give them enough energy and to last for a burst that is 5 milliseconds. But how do you generate this electric field? We don't really know. And then there is the problem with the bunches themselves. Like, yes, you could invoke the two-stream instability, but we're not exactly specifically sure of whether they are formed with that process or not? Can you form them in different ways? Is it stable enough? And these bunches, if you're bringing a lot of highly charged bunch together and squeezing it into a tiny space, there's a lot of repulsion between them. So they will disperse very, very fast. So there's also the problem with the dispersal of these bunches that they need to stay coherent for at least the pulse duration. And then because you're invoking radiation relatively close to the neutron star, then you have to deal with propagation through a dense magnetized plasma around it, which could essentially suppress a lot of radiation that these particles are emitting. And something that's characteristic with curvature radiation is that it produces a very broad spectrum. And that's not really what we currently see with FRBs. So you need to invoke even more constraints on the trajectories of the particles and the properties of the system to narrow down the spectrum. Okay, so most of these pulsar model problems were related to the fact that it was close to the actual neutron star. So how about we move that by quite a bit and move towards GRB-like models. So at least in one form of these models, what you have essentially is some magnetar or engine that's flaring for some reason due to crust cracking or magnetic field lines that intersect. And this sends out a flare of these charged particles. But then, as these travel through space, they will hit the old debris that was ejected from an older flare. And this would amplify the magnetic fields that are around the area, and these electrons will start gyrating around these magnetic fields. And for this, they could gyrate coherently and in phase, resulting in essentially just coherent cyclotron emission. And as this shock expands, you're moving towards regions of weaker magnetic fields, so your frequency also naturally drops with time. But this model still has a bunch of other drawbacks. This is also, I think, one of the simpler relativistic shock models. They can get quite complicated. But what this model requires is for these particles to emit coherently. Otherwise, you wouldn't meet the brightness temperature. So you need a highly ordered magnetic field in the upstream. Any sort of irregularities or perturbations in that would very much suppress the coherence of the emission and decrease your power quite significantly. So that sort of puts another constraint on your magnetic field, which is you need the plasma right after the shock to be cold. Because any sort of kinetic random motion will smear out the orderedness of the magnetic field. So this puts a constraint on, you can't see fast radio bursts right after each other, because then the plasma would be hot and the magnetic field would thus not be ordered enough for it to radiate coherently. And lastly, this process actually has a really relatively low radio efficiency in terms of its energy budget. So you need a larger amount of energy in the event that's driving this shock. So this sort of makes it even harder to generate something because you need to invoke something that's even more dramatic. So that's sort of us entertaining theorists, and which is fun. This is my favorite part about FRBs. And but other people choose sort of a different route to characterize FRBs, which is, well, we could just look for counterparts. That seems easy enough, maybe. So there have been a few counterparts that have been associated with FRBs. First are magnetars, which is great because a lot of the models require magnetars. And there was this burst that was associated with an X-ray burst from a galactic magnetar during one of its active phases. So people started freaking out and deep monitoring this magnetar by FAST, and they tried to look for any other confirmations of such associations. And, well, none were observed, which is great. And they concluded that magnetar, FRB, and hard X-ray bursts are kind of a rare association, and maybe we just got lucky. There have also been other counterparts or associations that were made where some of the FRBs were linked to persistent radio sources. And this sort of sparked this debate of FRBs being just a very specific channel of pulsar radiation that isn't driven by spin down, because it kind of resembles some of the giant pulses we see from the Crab pulsar, but this has not been really well studied enough, or like we haven't actually seen FRBs from such sources. So, open questions to essentially summarize this topic. I'll tell you about all the things I don't know, and I think most people don't know about fast radio bursts. And the first question that is quite fun to think about is, are FRBs really not repeated? Do such events exist, and why could they arise from different sources? What determines what makes an FRB a repeater versus not a repeater? And could they come from different engines? And then something that's perhaps harder to study is, how is FRB emission generated? You have one scale, which is, are we dealing with a shock, or are we dealing with like a magnetosphere flare, or like a pulsar-like mechanism? And then you have, what is the actual emission mechanism that's driving that? Is it sort of like coherent curvature radiation, or is it one of the other dozen mechanisms that you could have driving such stuff? So what mechanism produces this coherent emission that you see, and why does it go up to such high rates? And that's sort of what I had. You could very welcoming of more questions. That's always more like a lot of fun with FRBs. But yeah.
Thanks, let's give Nadine a hand. Any questions? So, you first.
Okay, yeah, I guess it's probably a hard question to like answer, but like, how would you go about searching for these in the sky? Like, a lot of the models you say propose magnetars, so you can maybe focus on some magnetars that you know of, but also that's not as super consistent with observation. So then how do you look for these things in the sky without just like staring at one tiny spot for a long time and then moving?
So I think a lot of people have been trying, like, you're essentially asking, how do you make associations?
Yeah.
That's really hard, because a lot of, like, the reason we associate it with a magnetar is because that pulse came from relatively nearby. So you can actually tell where it's coming from and associate it with other events. But a lot of these pulses are coming from really far away. So you could start by looking at the type of galaxy that it's in. How far away is it? So like, how high is the redshift, so you can kind of tell a little bit more about the environment that the source could be in. And you could also say, oh, is it coming from a star forming region, or is it coming from a really old region in the galaxy? And from like stellar evolution models, you can kind of deduce, okay, this can't be like this type of star, or that can be this type of engine. But that's essentially what we have. It's like maybe we'll get lucky and like get like a deadlock on something, but even if you do, that doesn't necessarily exclude any of the other models. Like you could have emission from multiple mechanisms and models. So it's looking more and
Okay. Also, another question is, you know, like a few years ago, I don't know if you said this. I think you said this. Like, we didn't like actually know of that many FRBs. I think like you said in 2011 we knew of like 4 or something.
yeah.
And now we know of like what, hundreds or more than 100. So what changed exactly?
So I think if I go with basically a lot more telescopes. So before we had like parks. Now you have parks, ASCAP, Arecibo, the GPT, and Chime, which is pretty much dedicated to just looking for FRBs. So you're essentially just spending more time looking for FRBs, while before it was looking through your past data to see if there were similar bursts that showed up. At least that's what I think.
Any other questions?
The reason Chime is focused on like the top right part of the sphere, or no?
I think it's just like the location it sees, like location of the actual telescope. So that's why you sort of have multiple ones, so you could cover a wider range of the sky.
So where can people go to read more about FRBs?
I think Nick and I have collected a wide range of review papers, and I could point you to a couple that I consider really nice reviews, and like go through the derivations of the physics and different models and discuss a lot of the pros and cons of the models. So it's an interesting read.
Are there any more telescopes that are going to be built in the future, the near future, to look for FRBs, or no?
I think essentially now people are trying to like localize stuff better. Is the DSA stuff gonna be looking for FRBs? I'm not sure exactly what their current plans are, but I think maybe. I think there's been a lot of attention and focus on FRBs because it's kind of like this $1 million question that could like crack something that's never been seen, and in science that's apparently great.
Yeah.
We like to answer questions, so I think there's a lot, especially given how much faster FRBs are being reported. There's a lot of money and work that's being directed towards them. So maybe we'll figure it out. Maybe they'll be like pulsars, and we'll be like, we don't have the technology to understand this, or maybe the physics can't be really like deciphered in a clear enough way.
Any other questions? Oh, yes.
Is there any some notable difference of radio spectra between non-repeating sources and just like single sources?
So the main differences are, I think, in the energetics. So the rotating sources, or at least if you're talking about like typical pulsars, their energy is from the spin down luminosities. That's a lot lower. And second is if you're detecting something from rotation, then it's gonna have a very specified clean period.
But I think the question is like difference between, are there any like other like qualitative differences between like
Observation
repeaters and
feature,
like?
you can actually see the difference between repeating sources and some sources not repeating.
Oh, I see. Sorry. So yes, kind of. Where so like repeaters are the ones where you see the sad trombone effect, and you also see some rotation measure variation. But I think it's hard to determine if this doesn't actually happen in non-repeaters, because with the repeaters you have much higher constraints on the data. So you can actually check for like really weak variations or like clean your data a lot better. But I think the sad trombone effect, some DM, some polarization angle swings that you see for rotators. But I think a lot of these are, you see changes between the different bursts. Maybe there's some stuff that are escaping my head right now.
I don't remember.
My second question is, if you just plot something like the populations of a redshift, you know, like that plot is gonna like grow over time if you get more observations, right?
Yeah.
So how's the trend right now? Is it just like pushing through the like far and far regions as we get more observations, or like just like piling up in like some regions? Or, yeah.
I think, so that's essentially like the Macquarie correlation, right?
Yeah, the correlation is, that's just like a relationship between DM and Z. I don't
Yeah.
actually know how far it is that we see them. Yeah.
I think I don't think we see them like at super
Yeah.
high redshift. But that could also be due to propagation or absorption or.
So we don't clearly know about that yet. Whether
I think that there is obviously a maximum Z that we've seen them at. I just don't remember what it is.
Yeah.
But
I was just wondering if there's constraining enough to conclude something like,
can't be.
okay, this is happening on some like mature galaxies or something.
Mhm.
Yeah.
Yeah, it's tough. There was one interesting source that was recently associated to a globular cluster in a different galaxy.
Mhm.
So like, you know, things like that. You know, maybe tell you about the environment. Who knows? Do you have a question?
Oh yeah. So the two models that you showed, they were like single system model in the sense they were single neutrons. So like, are there any models where they are binary systems, or have they all been like ruled out or something?
So there's still models. So here there's some models that invoke like a neutron star merger, where you have some interaction that generates FRBs during this down spiral. But you could also have just a stable binary where the field lines between these two neutron stars will accelerate particles along them, and then you can get curvature radiation from that. I think this is probably as much as I know about these models. But yeah, does that sort of answer your? There's like a whole Wikipedia page with all the different FRB mechanisms that like range from aliens to cosmic strings to weird flavors of black holes merging and.
Yeah. To be clear, this is not a page on Wikipedia. This is an entirely different wiki. that
Yeah.
has
Oh.
a page for every one of these things.
People on Wikipedia wouldn't allow that.
It's a very interesting scroll.
I'll vote for aliens.
Yeah, I'd vote for it
Yeah.
too.
There's a whole paper that I could direct you to that.
Oh yeah,
Studies
we
that.
we talked about there's a
Welcome to
paper.
read that.
There's a paper. Are you talking about the Jelinovich paper?
Yeah.
There's a paper which is basically like, what if FRBs are aliens that blow up planets?
Wow.
And then like I guess repeaters and non-repeaters correspond to like how much they want to blow up the planet or something. I think. something like that.
It's
That's cool.
They just have a Death Star.
Yeah,
And
exactly.
like, blowing up planets. That's what it is.
And they like simulate it and everything.
Yeah.
Blowing up rate.
Any other questions? All right, if not, let's thank our speaker again. So we actually have one more talk, which is 1 week from now, so it's also an unusual time. It's on Thursday. It's from a friend of mine who's gonna tell us about something, probably planets or astrochemistry related. And then after that, we will somehow resume our usual schedule, and we have some people after that. Thanks, everyone.